June 7, 1944. The cold waters of the English Channel lapped against concrete walls rising from the sea like monuments to an impossible dream. Lieutenant Colonel G.C.B. Shattuck of the Royal Engineers stood on what seemed to be solid ground, where only hours before there had been nothing but open water. Around him, hundreds of men worked frantically. They had 6 hours to turn theory into reality. 6 hours to build a harbour where no harbour existed. The invasion of Europe depended on it. The concept seemed mad to almost everyone who first heard it. 2 complete artificial harbours, each the size of Dover, would be prefabricated in Britain and towed across the Channel after D-Day. Winston Churchill had scribbled the directive that would define this moment years earlier. His words echoed in the minds of every engineer now racing against time. The piers must float up and down with the tide, and the difficulties will argue for themselves. Now those difficulties stood before Shattuck in waves that could destroy months of work in minutes. The tide would not wait. The enemy would not wait. History would not wait. The human dimension of this engineering marvel began not with blueprints, but with blood. August 19, 1940, Dieppe. The raid had been catastrophic. Over 3,500 Canadian soldiers killed, wounded, or captured. Churchill tanks foundered on shingle beaches, unable to move inland. The port itself remained firmly in German hands. But from that disaster emerged a single undeniable truth. The Allies could not capture a heavily defended port in the opening hours of an invasion. They would have to bring their own. The idea was so audacious that when Admiral Mountbatten first proposed it in 1942, he was met with hoots and jeers from seasoned military commanders. Yet here they were, 2 years later, making it real. The formal go-ahead came on September 4, 1943. The combined chiefs of staff estimated the artificial ports would need to handle 12,000 tons per day. In all weather conditions, the timeline was brutal. Production began in December 1943, just 6 months before D-Day. The objective was staggering. Offload 5,000 tons per day at Omaha Beach and 7,000 tons per day at Arromanches. No one had ever attempted anything remotely similar. The scale defied comprehension. From the summer of 1943, construction began in earnest, employing up to 45,000 personnel. Dozens of construction companies and 200,000 workers toiled at London, Tilbury, Woolwich, Barking, Portsmouth, Southampton, Middlesbrough, and other ports all over England. The workers themselves often had no idea what they were building. Security was absolute. A man might spend months fabricating steel pontoons without knowing they would form floating roadways in France. Another might pour concrete for massive caissons, without understanding they would become breakwaters protecting Allied supply ships. The secrecy was so complete that families living near construction sites were relocated. The whole area from Garliston through to the Isle of Withorn was declared off-limits. The technological challenge was unprecedented. To understand the Mulberry Harbors, one must grasp their fundamental components. Each harbour consisted of multiple integrated systems, each critical to the whole. The outermost defences were the bombardons, massive floating steel breakwaters shaped like crucifixes, anchored in deep water to blunt the force of waves before they could reach the harbour proper. These floating breakwaters comprised huge metal structures, firmly ballasted and anchored in place as the first line of defence against rough seas. Behind the bombardons came the Phoenix caissons, the engineering centrepiece of the entire operation. The largest Phoenix caissons were 200 feet long, 60 feet high, and weighed more than 6,000 tons. Each caisson weighed between 1,500 and 6,000 tons when constructed. The largest measured 60 by 17 meters and stood as tall as a 5-story building. These were not simple concrete boxes. They were hollow, watertight chambers that could float when pumped with air and sink when flooded with water. Around 2 million tons of steel and concrete were used in their construction. More than 213 Phoenix units were built, requiring over 1 million tons of reinforced concrete and 70,000 tons of steel reinforcement. Each caisson was equipped with aircocks that allowed engineers to control their descent to the seabed with precision. The construction of these giants presented immediate problems. In order to accommodate the construction of the massive phoenixes, excavators dug countless tons of dirt out of the banks of the Thames and Medway. In a dark irony of war, some 81,000 tons of rubble generated by the London Blitz was used to prepare yards to handle the project. The caissons were so massive that moving them required extraordinary measures. When the time came, more than 200 tugboats were needed to complete the task of towing them to assembly points. Then came the gooseberries, a simpler but equally essential component. 70 obsolete merchant vessels were assembled at Oban on the west coast of Scotland, stripped down, ballasted, and primed with explosive scuttling charges. These ships, codenamed corncobs, would make their final voyage under their own steam to be deliberately sunk in predetermined positions, creating additional barriers against the Channel's notorious storms. It was a practical solution born of necessity. There were not enough Phoenix caissons to protect both harbours fully, so obsolete ships would fill the gaps. The inner harbour required even more innovation. The pierheads, codenamed spuds, were floating platforms mounted on massive telescoping legs that rested on the seabed. In accordance with Churchill's directive, the piers did indeed float up and down with the tide, assisted by an ingenious system of hydraulic jacks. The legs could extend or retract to accommodate the extreme tidal range of the Normandy coast, which exceeded 20 feet between high and low tide. Ships would moor alongside these spuds to unload their cargo. Connecting the spuds to the beach were perhaps the most elegant components: the whale roadways. 10 miles of floating roadway would require 120 80-foot spans and 670 floating pontoons called beetles. Lieutenant Alan Beckett of the Royal Engineers designed these remarkable structures. The whales were flexible steel bridges mounted on pontoons that could articulate up to 24 degrees with the waves. The entire system was designed to remain functional regardless of tide or sea state, allowing vehicles to drive from ships directly onto French soil without ever getting wet. But creating these components was only the first challenge. They had to be tested under conditions that approximated combat reality. Sections were floated up the coast to Garliston in Wigtown Bay near Dumfries in Scotland, identified as a suitable test beach given its characteristics similar to Normandy: flat, sandy, remote, and sparsely populated. Prototypes of each design were built and transported to the area for testing by Royal Engineers based at Cairnhead and in Garliston. The tests revealed serious problems. The Swiss roll design, a flexible timber and canvas roadway, could only handle trucks up to 7 tons in the Atlantic swell. Then nature provided the ultimate test. A severe storm struck the test site, undermining the hippo pontoons and causing the crocodile bridge spans to fail. The Swiss roll washed away entirely. Only Beckett's whale roadway survived undamaged. The human stories behind these tests reveal the pressure engineers faced. Major Scott Bowden and Sergeant Ogden Smith of the Royal Engineers embarked on what may have been the war's most nerve-wracking reconnaissance mission. On New Year's Eve 1943, they were landed on Gold Beach at Luc-sur-Mer under cover of darkness and took samples of sand. They worked in silence within yards of German sentries, scooping sand and gravel into containers. The geological data they gathered would determine whether the harbour components could be anchored securely or would sink into the seabed. One wrong sound, one alert sentry, and the mission would fail. They made it back. Their samples showed the seabed could support the massive weight of the Phoenix caissons. Between November 1943 and January 1944, the 712th Survey Flotilla used specially adapted landing craft personnel large to survey the Normandy coast under the noses of German defenders. These small boats ventured out on moonless nights, taking depth soundings and mapping underwater topography. The first sortie, Operation KJF, occurred on the night of November 26-27, 1943, when 3 craft took measurements off Arromanches. A follow-up mission to survey the Omaha Beach area on December 1-2 encountered navigation problems, and the team sounded an area more than 2,000 yards west of the intended location. They had to return on December 28-29 to complete the task correctly. Each mission risked capture or death. The hydrographers persisted because they understood that inaccurate data would doom the entire operation. As spring 1944 approached, the construction effort reached fever pitch. The challenges multiplied. Building bombardons caused unwanted secondary effects. The use of dry docks for bombardons meant they were unable to be utilized for Phoenix construction. The King George V dry dock in Southampton could build 8 Phoenix caissons simultaneously, but was tied up with bombardon work. Brigadier Bruce White, the Royal Engineer leading the project, protested repeatedly that the bombardons were unnecessary. The Admiralty overruled him. The floating breakwaters were built anyway, consuming precious resources and construction capacity. Under White's leadership, the entire project was concluded in a startlingly short 8 months, without a serious breach of the tight security surrounding it. White was a World War I veteran who had pioneered port operations and electric cranes at Richborough Castle in Kent during the previous conflict. He understood logistics in ways few men did. He also understood that the Mulberry project was not just an engineering challenge, but a race against German intelligence. Every day of construction risked exposure. Lord Haw, the Nazi propagandist, demonstrated how close the Germans came to understanding Allied intentions. In May 1944, William Joyce told British listeners, "We know what you're doing with those caissons. You intend to sink them off the coast when the attack takes place. Well, chaps, we've decided to help you. We'll save you trouble and sink the caissons before you arrive." The threat was real. German long-range artillery at Calais could reach some of the assembly points. Deliberate deception operations stored harbour components within range of German guns to suggest an attack near Calais rather than Normandy. The completed components presented a logistical nightmare of their own. Phoenix caissons were moored in rivers and estuaries around southern England, waiting for D-Day. Then disaster nearly struck. One of the massive Phoenix units went aground at the Brambles near Southampton. Engineers began pumping it out to refloat it and discovered their pumps were completely inadequate. The supplied pumps were designed for moving large volumes of sewage horizontally and were incapable of providing the necessary lift to pump water up and out of the caissons. Churchill himself intervened, taking the refloating task away from the Royal Engineers and assigning it to the Royal Navy. Rear Admiral Edward Ellsberg, a renowned salvage expert, was brought in. He identified the problem immediately and requisitioned heavy-duty pumps from across Britain. The Phoenix was refloated, but the incident revealed how close the entire operation came to failure, due to seemingly minor oversights. Then came June 6, 1944. Early on the grey, chill morning of Tuesday, the British, American, Canadian, and Free French assault troops waded ashore on Gold, Juno, Sword, Utah, and Omaha beaches. The world watched the infantry charge up the beaches. Behind them, unseen by most, began the largest engineering operation in military history. The first boats destined for the harbour set out from England on June 4th. Most were positioned about 5 miles off the coast of France when the invasion began. Within hours of the Allies creating beachheads after D-Day, sections of the 2 prefabricated harbours were towed across the English Channel from southern England. The first convoy of 45 blockships arrived in the assault area at 12:30 p.m. on June 7th, and the sinking of vessels was started at once. The corncob ships made their final voyage to predetermined positions. Explosive charges detonated. Ships that had sailed the Atlantic for decades settled into the sand of Normandy's coast, their sacrifice creating protective barriers for the vessels that would follow. The rest of the Mulberry sections followed in a round-the-clock effort. Convoys of 8 Phoenixes, 8 bombardons, 4 pierheads, 10 whale roadways, and 2 miscellaneous units were towed across the choppy channel by the tug fleet at 4.5 knots to reduce turnaround time. Construction of the breakwaters began on D-Day itself. The bombardons anchored on June 6th, and the first Phoenix caissons were installed on June 9th. Royal Engineers worked under fire, guiding the massive concrete structures into position. All of the corncob ships were sunk by June 10th, and the entire breakwater was completed on June 11th, just 5 days after D-Day. By June 13th, Mulberry B was established to the extent of providing 2 crescent-shaped harbours, which could accommodate up to 75 Liberty ships and smaller craft. Within 6 days, Mulberry B was operational. The speed was extraordinary. A harbour the size of Dover, built from scratch in a war zone in less than a week. But Mulberry A at Omaha Beach developed more slowly. The American engineers faced different challenges. The beachhead at Omaha had been nearly lost on D-Day itself, and German artillery continued to harass the construction crews. By June 9th, just 3 days after D-Day, 2 harbours codenamed Mulberry A and B were under construction at Omaha Beach and Arromanches. Then, on June 19th, 13 days after the invasion, nature delivered a blow more devastating than any German counterattack. Major Ronald Cowan of the Royal Engineers reported it was a storm such as had not been seen in the Channel for 80 years, second only to the one that smashed the Spanish Armada in 1588. For 4 days, winds screamed like a banshee as great waves crashed into the harbours, damaging pierheads, washing over and sinking pontoons, twisting piers, dragging anchors, and casting landing craft and vessels adrift. Lieutenant Colonel Raymond Mays, in charge of the piers and pierheads, issued emergency orders as the storm built. Moorings were doubled. Ships outside the harbors were moved clear of the breakwaters. Tugboats were provisioned for rescue operations. 500 landing craft sheltered inside the Arromanches harbor, protected by the blockships and caissons. But at Omaha, the destruction was catastrophic. Mulberry A was not as securely anchored to the seabed as Mulberry B had been by the British, resulting in severe damage during the Channel storm of June 19, 1944, that it was considered irreparable and its further assembly ceased. 21 of the 28 Phoenix caissons had been wholly destroyed. The bombardons were adrift. The roadways and piers had been smashed. The American harbor, that had taken 8 months to design and build, was obliterated in 4 days. Parts of the wreckage were salvaged to repair the British harbor at Arromanches. Mulberry B survived, but with damage. The storm tested every engineering decision made over the previous year. The Phoenix caissons, anchored more securely than their American counterparts, held. The blockships absorbed wave energy. The whale roadways, designed to articulate with the swells, bent but did not break. Yet the storm revealed a fatal flaw in the bombardon design. Some of the floating breakwaters sank, others broke loose and caused more damage to the harbor than the storm itself might have inflicted. Brigadier White's protests about the bombardons had been vindicated, but too late to matter. In the aftermath, a critical decision faced Allied commanders. Should they rebuild Mulberry A? Could they even sustain the invasion without it? The answer came from an unexpected source: the beaches themselves. American forces at Omaha and Utah discovered they could offload supplies directly onto the beaches at rates approaching what the Mulberry harbors were designed to achieve. The vast resources used on the Mulberry may have been wasted, as American forces were supplied mostly over the beaches without the use of a Mulberry right through to September. It was a sobering realization. The engineering marvel that consumed millions of tons of concrete and steel might have been unnecessary. But Mulberry B told a different story. Port Winston saw heavy use for 8 months, despite being designed to last only 3 months. After June 20th, the harbor itself was unloading 6,750 tons a day. In the 10 months after D-Day, it was used to land almost 3 million men, 4 million tons of supplies, and 500,000 vehicles to reinforce France. The numbers were staggering. 2.5 million men, 500,000 vehicles, and 4 million tons of supplies landed in Europe through the artificial harbor at Arromanches. In response to this longer-than-planned use, the Phoenix breakwater was reinforced with the addition of specially strengthened caissons. The scale becomes comprehensible only through individual examples. Every day, Liberty ships approached Port Winston and moored at the spuds. Cranes swung cargo nets loaded with ammunition onto the whale roadways. Trucks drove across the floating bridges, tires gripping steel mesh as the roadway rose and fell with each wave. Sherman tanks rumbled from ship to shore without touching water. Behind them came jeeps, half-tracks, artillery pieces, ambulances and supply trucks carrying everything from blood plasma to jerry cans of fuel. A typical serviceman needed 6.5 pounds of supplies per day to keep him effective in the field. On D-Day, over 150,000 men landed on the 5 beaches, requiring well over 400 tons of supplies per day just to sustain them. By the time Operation Neptune ended, over 1 million men had landed in Normandy, demanding 3,000 tons of consumable supplies per day. The engineers who maintained Port Winston worked around the clock. Tidal variations meant the pierheads had to be adjusted twice daily. Salt water corroded steel components that had to be repaired or replaced. Cables wore through and had to be spliced. Pontoons took on water and had to be pumped. It was unglamorous work, performed by men whose names would never appear in history books. Mulberry B was operated by 20 Port Group Royal Engineers, under the command of Lieutenant Colonel G.C.B. Shattuck. These engineers understood that every delay in unloading meant soldiers at the front went without ammunition or food. They worked through exhaustion, through German air raids, through the constant fear that another storm would destroy what they had built. The harbor's success depended on integration of all components. If the Phoenix caissons failed, waves would swamp the pierheads. If the pierheads jammed, ships could not unload. If the whale roadways broke, vehicles could not reach shore. Every element had to function perfectly for the system to work. This interdependence reveals why the Mulberry harbors represented such a significant engineering achievement. It was not just the size of individual components, but their orchestration into a functioning whole. By November 1944, Allied forces had captured the port of Antwerp. The harbour was decommissioned 6 months after D-Day, when Allied forces could use the recently captured port of Antwerp to offload troops and supplies. Port Winston had served its purpose. The massive Phoenix caissons remained in place, too difficult to salvage. Today, they still sit off the coast of Arromanches, visible at low tide, concrete monuments to what was accomplished. The historical aftermath of the Mulberry Harbors extends beyond their immediate function. They represented a fundamental shift in amphibious warfare doctrine. Before Normandy, military planners assumed that capturing a port was the essential first objective of any large-scale invasion. The Mulberry experience demonstrated that forces could be supplied over open beaches for extended periods, given sufficient engineering preparation and logistical organization. This realization influenced every subsequent amphibious operation of the war. The engineering lessons were equally profound. The storm that destroyed Mulberry A taught designers that flexibility and redundancy mattered more than raw strength. The whale roadways survived because they could bend. The Phoenix caissons held because they were over-engineered. The bombardons failed because they were too rigid. These lessons applied far beyond harbour construction. They influenced bridge design, offshore oil platforms, and coastal engineering projects for decades after the war. The cost of the Mulberries, both financial and material, sparked debate even before the war ended. The estimated price tag for the enterprise was a staggering $25,000, equivalent to $912,342 today. Critics pointed out that American forces supplied themselves effectively without an artificial harbour after Mulberry A's destruction. They questioned whether the resources consumed by the Mulberry project might have been better spent on other war needs. Defenders countered that Port Winston's contribution was undeniable, and that the availability of the harbours influenced the decision to proceed with the invasion in June, rather than waiting for better weather later in the summer. The human cost was less tangible but equally real. Engineers worked under combat conditions for months. Some were killed by German artillery or air attacks. Others died in accidents, crushed by shifting caissons or drowned when pontoons capsized. The exact number of casualties among the construction crews was never compiled, but memorials in Arromanches honour the engineers who died building and maintaining Port Winston. Their sacrifice receives less attention than the infantry who stormed the beaches, but without them, those infantrymen would have been stranded without support. The German perspective on the Mulberry Harbors offers perhaps the most telling assessment. Albert Speer, Nazi Germany's former armaments minister, said after the war, "To construct our defences in 2 years, we used 13 million cubic metres of concrete and 1.5 million tons of steel. A fortnight after the landings by the enemy, this costly effort was brought to naught by an idea of simple genius." Speer understood what the Mulberries meant. Germany had spent years fortifying ports, believing that controlling those ports would prevent invasion. The Allies simply bypassed the entire problem by building their own ports. It was not brute force that defeated the Atlantic Wall, but lateral thinking applied through systematic engineering. The technical achievement of the Mulberry Harbors rested on thousands of individual innovations. Consider the kite anchors designed to hold the whale roadways in position against channel currents. Each anchor had to be strong enough to resist wave action, yet deployable by small crews in combat conditions. Or the hydraulic systems that allowed the spuds to rise and fall with the tide while remaining perfectly level. Engineers designed these systems using 1940s technology, slide rules, drafting tables, and practical experience rather than computer simulations. Every calculation was done by hand. Every stress analysis required manual computation. The margin for error was zero, because there would be no opportunity to test the full system until it was assembled under fire on the French coast. The manufacturing challenge matched the engineering difficulty. Full-scale production involved some 50,000 tons of fabricated steelwork and the participation of over 200 companies across England and Wales to complete the work on schedule. These companies had to coordinate production of components that would fit together perfectly despite being manufactured in separate locations. A Phoenix caisson built in Southampton had to make precisely with whale roadway sections built in Birmingham and pierheads fabricated in Newcastle. There was no opportunity for trial assembly. Everything had to work correctly the first time. The workers themselves came from every sector of British society. Steelworkers, shipbuilders, carpenters, concrete workers, welders and labourers all contributed. Many were women, filling roles left vacant by men serving in combat units. They worked 12-hour shifts in all weather. knowing that delays would cost lives when the invasion came, but not knowing when that would be. The strain of sustained maximum effort over months wore people down. Injuries increased as fatigue set in, yet productivity never faltered. Britain in 1943 to 1944 was a nation mobilized for total war, and the Mulberry Project benefited from that mobilization. Security concerns created constant tension. Workers signed official secrets acts, but were told nothing about the purpose of what they built. Supervisors knew more but were forbidden to discuss it. Engineers understood the full scope but lived in fear that German intelligence would discover the plan. MI5 officers interrogated anyone showing undue curiosity. When code words including Mulberry appeared in Daily Telegraph crossword puzzles in the month before invasion, MI5 questioned the crossword compiler, Headmaster Leonard Dorr. Many years later, one of Dorr's students revealed the teacher often asked for words for his puzzles from pupils in his classes, many of whom lived near US military barracks. It was coincidence, but it demonstrated how close security came to being breached. The technical specifications of Port Winston reveal engineering at the edge of what was possible in 1944. Each Mulberry was designed to be about a mile long and stand about 30 feet above sea level. At low tide and 10 feet at high tide, the depth of water at the pierheads had to accommodate Liberty ships with drafts of 26 feet when fully loaded. This meant the Phoenix caissons had to rise 60 feet from the seabed to provide adequate shelter at high tide. The harbors consisted of around 6 miles of flexible steel roadways floating on steel or concrete pontoons. Every connection point between components had to allow for movement while remaining watertight. Salt water, wave action, and tidal forces constantly stressed every joint and fastener. The logistics of moving the Mulberry components across the channel tested the limits of available resources. On the afternoon of June 6th, over 400 towed component parts weighing approximately 1.5 million tons set sail to create the 2 Mulberry harbors. This fleet required coordination of hundreds of tugboats, pilot boats, and escort vessels. Routes had to be cleared of mines. Navigation had to be precise enough to deliver each component to its designated position. Weather had to be monitored constantly, because towing massive caissons in rough seas risked capsizing or breaking tow cables. The entire operation resembled an industrial assembly line stretched across 100 miles of open water, operating under threat of German attack. The assembly process on the French coast required engineers to work with extraordinary precision under chaotic conditions. German artillery still fired on the beaches. Aircraft strafed vessels. Tides shifted component positions. Yet engineers had to position Phoenix caissons within feet of predetermined locations, align pierheads precisely with approach lanes, and connect floating roadways at exact angles. Survey teams worked from small boats, taking measurements and directing tugboat crews. Divers descended to inspect caisson positions and anchor placements. The entire operation resembled building a skyscraper, while the foundation constantly shifted. Communication breakdowns threatened the operation repeatedly. British and American forces used different radio frequencies and code words. Tugboat crews often could not communicate directly with the engineers directing them. Weather forecasts proved unreliable. The famous chaff meteorologist James Stagg had predicted the brief clear period that allowed D-Day to proceed. But forecasting the June 19th storm proved more difficult. Some indicators suggested bad weather, but the severity caught everyone by surprise. Better communication might have allowed engineers to take additional protective measures before the storm hit. The human resilience demonstrated during the storm deserves recognition. Engineers who had worked without sleep for days continued working throughout the 4-day tempest. They reinforced moorings, adjusted tensions on anchor cables, and directed rescue operations for vessels driven aground. When the storm finally passed, they immediately began repairs without waiting for orders. The speed with which Port Winston returned to full operation after the storm demonstrated not just engineering, competence, but human determination. Comparing the fate of Mulberry A and Mulberry B reveals subtle but significant differences in construction approach. Mulberry A was not as securely anchored to the seabed as Mulberry B had been by the British. This difference may have resulted from time pressure. American forces needed their harbour operational as quickly as possible to support the drive inland. British engineers took slightly longer to position and anchor their components, but created a more resilient system. The lesson was clear. In complex engineering projects, shortcuts taken to save time often cost more in the long run. The technological legacy of the Mulberry Harbors extends into the present day. Modern offshore construction, from oil platforms to wind farms, uses techniques pioneered during the Mulberry Project. The concept of floating structures anchored to the seabed in deep water traces directly back to the spuds and phoenix caissons. The use of flexible connections between rigid components, demonstrated by the whale roadways, informs modern bridge and pipeline design. Even the logistics of the operation, coordinating vast numbers of components manufactured in dispersed locations for assembly at a distant site, presaged modern just-in-time manufacturing and global supply chains. The psychological impact on German defenders watching the harbours materialized deserves consideration. Imagine being a German soldier stationed on the Norman coast, having repelled the initial invasion at great cost, expecting the Allies to wither without supplies. Instead, within days, complete harbours appeared offshore. Ships that should have been vulnerable to shore batteries sheltered behind breakwaters. Vehicles that should have struggled through surf drove to shore on roadways. The message was unmistakable. The Allies possessed industrial capacity and engineering expertise that Germany could not match. The Mulberry Harbours were psychological warfare as much as logistical tools. 8 caissons from the Mulberry Harbours found an unexpected second life after the war. The Netherlands, facing catastrophic flooding risks, purchased 8 Phoenix caissons from the British Admiralty. These massive concrete structures were towed to the Netherlands and incorporated into the Delta Works, the comprehensive flood protection system built after the devastating 1953 floods. Today, visitors to the Watersnood Museum can walk inside these same caissons that once protected Allied supply ships off Normandy. It is a poignant reminder that engineering designed for war can serve peace. The men who designed the Mulberry Harbours came from disparate backgrounds but shared certain characteristics. Churchill's vision and political support proved essential. Without his backing, the project would have died in committee. Brigadier Bruce White brought practical experience and organizational genius. Lieutenant Alan Beckett contributed creative engineering solutions. Hugh Iris Hughes provided structural expertise. Admiral Hickling coordinated naval operations. Each contributed essential elements, but none could have succeeded alone. The Mulberry Harbours emerged from genuine collaboration, not individual brilliance. The testing phase at Garliston, though far from the battlefield, involved real risk. Engineers tested components to failure because they had to know the breaking points. When the Swiss roll design washed away in the Atlantic storm, engineers lost months of work but gained invaluable knowledge. When the Crocodile Bridge spans failed, designers returned to their drawing boards and created better solutions. The willingness to accept failure during testing saved lives during the actual invasion. This principle, test to failure in controlled conditions, to prevent failure in combat, became a cornerstone of military engineering. The weather forecasting for the Mulberry operation deserves closer examination. The invasion date depended on tides, moonlight, and weather conditions aligning within a narrow window. The storm of June 19th occurred just 13 days after D-Day, within the period when Allied forces remained most vulnerable. Had the storm struck a week earlier, it might have prevented the invasion entirely. Had it struck 2 weeks later, sufficient supplies might have been stockpiled ashore to weather the interruption. The timing was catastrophically unlucky, yet the operation survived. This resilience testified to the robustness of the engineering and the adaptability of the forces using the harbours. The relationship between the Mulberry Harbours and the broader logistics network requires understanding. Port Winston was not the only supply route. The beaches themselves continued to operate. Small ports like Courseulles were captured and put into service. The famous Red Ball Express truck convoys began running supplies inland. Port Winston was the largest single component of a complex system, but it functioned as part of that system rather than independently. When the harbour operated at peak efficiency, the entire supply network benefited. When storm damage reduced capacity, other routes compensated. This redundancy was deliberate. Planners understood that no single point of failure could be permitted. The reconstruction of the German perspective on the Mulberry Harbours reveals significant intelligence failures. Despite Lord Hawhor's broadcasts suggesting German awareness, actual German responses indicate confusion. Coastal batteries shelled the harbour construction, but without systematic targeting. Luftwaffe attacks were sporadic and ineffective. U-boats that might have targeted the slow-moving tow convoys crossing the channel were largely absent. German forces seemed unable to comprehend the scale or significance of what they witnessed until too late. This failure stemmed partly from the success of Allied deception operations suggesting an invasion near Calais, but also from a fundamental inability to imagine engineering on such a scale. The Allied bomber offensive against German industry created conditions that made the Mulberry Harbors possible. German aircraft production focused on defensive fighters to protect the Reich. German steel went to U-boats, tanks, and fortifications. German concrete reinforced the Atlantic Wall. Meanwhile, British and American industry operated at near maximum capacity, protected by distance from bombing. The Mulberry Harbors represented not just engineering achievement, but industrial dominance. They were constructed because the Allies could afford the resources while Germany could not. The human stories from Port Winston's operation reveal the daily reality behind the statistics. Merchant sailors who survived U-boat attacks in the Atlantic arrived at Arromanches to unload cargo, only to face German artillery fire. They had no combat training, no weapons, only the knowledge that the supplies they carried might save lives at the front. Tugboat crews maneuvered massive caissons and pierheads in heavy seas, knowing that one miscalculation could capsize their boat or crush them between concrete and steel. Medical personnel established aid stations on the pierheads to treat injured dock workers and sailors, working in the open with minimal shelter. These individuals performed unglamorous but essential work, often in danger, rarely recognized. The technological limitations of 1944 made the Mulberry achievement even more remarkable. No computers calculated stress loads or simulated wave action. Engineers used empirical formulas, practical experience, and scale models. Testing required building full-size prototypes, because small-scale models could not accurately predict how massive structures would behave in actual seas. Every design decision involved calculated risks because perfect information was impossible. Modern engineers reviewing the Mulberry plans with contemporary analysis tools consistently express amazement that the harbors worked at all given the limitations designers faced. The environmental impact of the Mulberry Harbors, while not a concern in 1944, provides interesting retrospective insight. The Phoenix caissons remain off Arromanches today, creating artificial reefs that support marine ecosystems. The deliberate sinking of the corncob block ships created similar habitat. During construction and operation, the harbors certainly disrupted local fishing and coastal ecosystems. The petroleum spilled from damaged vessels contaminated beaches and coastal waters. Yet compared to the overall environmental devastation of war, these impacts were minor. The concrete caissons, built to last 3 months, have now endured 80 years and will likely remain for centuries more. The financial accounting of the Mulberry project reveals interesting priorities. £25 million in 1944 represented an enormous sum, yet it was approved without significant debate. By comparison, the entire British aircraft industry budget for 1944 was approximately £40 million. The Mulberry project consumed resources equivalent to more than half the nation's fighter production for a year. This allocation reflected Churchill's conviction that logistics would determine victory. He was willing to sacrifice other capabilities to ensure that once Allied forces landed in France, they could be sustained. The interaction between British and American approaches to the Mulberry construction offers lessons in alliance management. British engineers designed most of the components and took primary responsibility for construction. American industrial capacity contributed materials and manufacturing. When Mulberry A was destroyed, there was no recrimination or blame. American forces simply adapted, proving they could sustain themselves through beach landings. British forces continued using Port Winston, proving its value. Both approaches worked, validating the decision to pursue multiple logistical strategies simultaneously. The role of Canadian forces in the Mulberry story deserves mention. Canadian engineers participated in the construction and operation of Port Winston. Canadian ships towed components across the channel. Canadian troops landed across the beaches supplied through the artificial harbour. The Dieppe raid that helped convince planners of the need for artificial harbours had cost Canadian lives. In a sense, the Mulberries represented both a memorial to those losses and vindication of the lessons learned through sacrifice. The timing of the harbour's decommissioning in November 1944 marked a transition in the European campaign. By that point, Allied forces had broken out of Normandy, liberated Paris, and were driving toward Germany. The capture of Antwerp provided a deep water port closer to the front lines. Port Winston's mission was complete, but its contribution had been indispensable. The harbour had bought time for Allied forces to establish themselves in France. Without it, the period between D-Day and the capture of major ports would have been far more precarious. The preservation of mulberry remnants at Arromanches creates an unusual memorial. Most war memorials are deliberately constructed monuments. The phoenix caissons off Arromanches are functional artifacts accidentally preserved. Tourists today can see them from the beach at low tide, walk among them when the water recedes, and touch concrete poured in England 80 years ago. Museums in Arromanches display models and photographs, but the actual harbour components visible offshore provide a tangible connection to history that few memorials offer. The strategic deception surrounding the Mulberry Harbors extended beyond concealing their purpose. Components were deliberately positioned to suggest attacks in multiple locations. Some caissons were moored near Dover in positions visible from German reconnaissance aircraft. Others were hidden in rivers and estuaries where they would not be detected. The balance between hiding components and using them as deception required careful calculation. Too much concealment would have been impossible given the massive scale. Too much visibility would have revealed Allied intentions. The compromise achieved, keeping the project known but its purpose obscure, demonstrated sophisticated intelligence operations. The human cost of the June 19th storm extended beyond damage to equipment. Sailors died when landing craft broke loose and capsized. Engineers were swept overboard from pierheads. Tugboat crews vanished when their boats foundered. The exact casualty figures from the storm were never compiled separately from overall D-Day campaign losses, but survivors' accounts make clear that men died trying to save the harbours. Their names appear on no memorials because they were not killed in direct combat, yet their deaths were equally the result of war. The technical evolution of harbour engineering since 1944 owes much to lessons learned from the Mulberries. Modern floating offshore platforms use variations of the Phoenix caisson concept. Oil rigs employ similar ballasting systems to sink structures to the seabed, then deballast them to create buoyancy for removal. The massive floating dry docks used for ship construction and repair evolved from techniques pioneered for the spuds and their telescoping legs. Even modern container ports employ variations of the flexible causeway concept, using floating pontoons to accommodate ships of different sizes. The psychological burden on engineers responsible for the Mulberry project must have been immense. They knew that design failures would kill people. They knew that delays might cost the war. They knew that untested components had to work perfectly the first time under combat conditions. This pressure produced both brilliance and occasional breakdown. Some engineers suffered what would now be recognized as stress-related disorders. Others thrived on the challenge. The diversity of human responses to extreme pressure reveals itself in the Mulberry story as much as in combat narratives. The integration of civilian expertise into military operations, exemplified by the Mulberry Project, became standard practice after World War II. Before the war, military engineering largely relied on service personnel with limited civilian input. The Mulberries required expertise that simply did not exist within military establishments. Civilian bridge engineers, harbour designers, structural specialists, and construction managers were recruited and given military ranks or civilian consultant status. This cross-pollination of military and civilian expertise produced better results than either community could have achieved alone. The manufacturing tolerances required for Mulberry. Components pushed 1940s industrial capability to its limits. Phoenix caissons had to be watertight, despite being assembled from hundreds of individual concrete pours. Steel pontoons had to be fabricated with sufficient precision that connection points would align, despite being manufactured in different facilities. The roadway segments had to fit together with minimal gaps to provide smooth surfaces for vehicles. Achieving these tolerances with wartime materials and fatigued workers required extraordinary quality control. Inspection teams checked every weld, every concrete pour, every connection point. Rejected components had to be rebuilt, consuming additional time and resources. The propaganda value of the Mulberry Harbors was recognized but never fully exploited. Photographs of Port Winston in operation appeared in newspapers and newsreels, demonstrating Allied capability. Yet security concerns limited detailed disclosure. The full scope of the engineering achievement could not be revealed without compromising valuable information about Allied capabilities. Only after Germany's defeat did the complete story emerge. This delay meant that public appreciation of the Mulberries came retrospectively, rather than building morale during the war. The environmental conditions at the Normandy coast imposed unique constraints on the harbour design. The Atlantic coastline experiences stronger wave action than the Mediterranean or Pacific theatres. Tidal ranges along the Normandy coast exceed 20 feet, among the highest in Europe. Strong currents flow parallel to the shore. Storm frequency in the English Channel averages higher than most coastal areas. Every one of these factors required specific engineering responses. The Mulberry design that worked at Arromanches would have been overbuilt for calmer waters and inadequate for more severe conditions. The design was bespoke to its location, not a universal solution. The comparison between the Mulberry Harbors and other major engineering projects of World War II provides context for their significance. The Manhattan Project consumed more resources and involved more scientists, but produced a single weapon used twice. The Burma Road sustained Chinese resistance but served a secondary theater. The Alaska Highway connected existing infrastructure across remote terrain. The Mulberry Harbors were unique in combining massive scale, innovative design, accelerated timeline, and direct impact on the war's primary theater. Few engineering projects in history have met such demanding criteria. The aftermath for individual engineers involved in the Mulberry Project varied widely. Some received honors and recognition. Brigadier Bruce White was knighted for his contributions. Alan Beckett returned to civilian engineering practice. Others faded into obscurity, their contributions known only to specialists. The disparity between contribution and recognition affected many participants. Engineers who designed critical components received less public acclaim than military commanders who used the harbors. This pattern repeated throughout the war, with logistics and engineering achievements overshadowed by combat narratives. The German failure to develop equivalent technology reveals different strategic priorities and capabilities. Germany excelled at tactical innovation, new weapons, new tactics, new formations. German engineers designed revolutionary aircraft, rockets, and tanks. But Germany never matched Allied strategic logistics. The Mulberry concept required thinking beyond immediate tactical needs to long-term operational sustainability. It required committing massive resources to infrastructure rather than weapons. German military culture and strategic circumstances made such investment unlikely, even had they conceived the idea. The Mulberry Harbors represent perhaps the clearest example of World War II, victory through industrial capacity rather than military genius. The invasion plan was not particularly sophisticated. The combat tactics were proven but conventional. What made Normandy decisive was the ability to land overwhelming force and sustain it indefinitely. The Mulberries were the physical manifestation of this capability. They announced to Germany that Allied resources were effectively unlimited, that no defensive position was secure, and that industrial might would determine the war's outcome. Now, 8 decades later, the concrete caissons still visible off Arromanches stand as monuments to a peculiar form of human achievement. They represent victory, certainly, but also the transformation of war into an industrial process. They demonstrate ingenuity, but ingenuity in service of destruction. They show what humans can accomplish when necessity demands, but the necessity was born of conflict that killed millions. The remains of Port Winston are simultaneously inspiring and sobering, testaments to both human capability and human cost. The engineers who built the Mulberry Harbors worked without glory, often without recognition, sometimes without even knowing the purpose of their labor. They poured concrete, welded steel, assembled pontoons, and tested prototypes in Scottish bays. They did not storm beaches or fly combat missions. They turned abstract plans into functional reality through skill, persistence, and unheralded sacrifice. The 6 hours that Lieutenant Colonel Shattuck and his engineers had to make the harbour operational stretched into days and months of continuous effort. But in those first 6 hours, when the future of the invasion hung in the balance, they proved that Churchill's impossible vision could be real. They built a harbour where no harbour should exist, and through it flowed the tide that would liberate Europe. Their legacy is written in concrete and steel, slowly eroding in the Norman surf, gradually returning to the sea that once yielded to their engineering will.